guys, welcome back. Um, we were discussing the inverter step response, the inverter's response to a step input, and yeah, we were at the beginning. Okay, the inverter is shown here on the right, and you can see that it is driving a load capacitor, C load. Okay, so as we said, it will take some time to charge and discharge the capacitance. And let me write down the equation for that. Okay, the capacitance current, or the capacitance, let's say, current flowing through the capacitance will be called IC is going to be what? C dVc over dt. Okay, it's going to be a differential equation. Okay, it's the derivative of the voltage multiplied with the capacitance will determine the current. Or if current is determined is a fixed value, then or is the determining value, then the capacitive voltage will change based on this equation. Now, and this inverter is going to be driving this, and we are applying a step input. A step input means that my input is 0 and then goes to 1 abruptly. Okay, 0 and it goes to VDD. Okay. And so what's happening when the input is 0, basically the MOS transistor is off and the PMOS transistor is on. And when the input is VDD, what will happen is the PMOS transistor will turn off, okay, and the only transistor that is on will be my MOS transistor, and it will start discharging the capacitor charges on my capacitor. Okay, so current will be flowing through my capacitor and through my transistor. So basically, IC will be equal to the transistor current. Now let's write down the equation and say that, okay, this event is happening at T0, okay, and the mathematical expression for this one is going to be T0, okay, times dt. And what will happen, what is happening to my output voltage value before T0? If my input is 0, the output is at VDD. This is going to be what? Before T0, T less than T0 will be what? VDD. Okay. And what will be happening to my output voltage after the step input? Okay, after T0, it's going to change within time. Okay, it's going to be what? This is of course after T0. Okay, it's going to be what? It's basically going to be this value. Okay, this is the output here, and this is my IDS. IDS is going to be equal to C dV out. As you can see, the capacitive voltage capacitance across the place of my capacitor. Now the voltage across the place of my capacitor is V out, dV out over dt. And if you take the capacitor value to the other side, you will end up with this equation here, okay, which is going to be IDS T divided by capacity, okay. Then what is IDS and T? Okay, what is IDS and T? We have to write the equations. We know we are going to be using the Shockley model, the the first order approximation of the current voltage relationship for the transistor. So before T is equal to T0, what is the case? Then the input is 0 volts, hence the transistor is in cutoff, so IDSN is basically 0 volts. Okay? 0 amperes. And when V out is greater than VD minus, this is my VGS, by the way. Okay, this is my VGS. VGS. Okay, VGS minus VT is what? Is VSAT. Okay, so basically, when V out is greater than VSAT, I am in the saturation mode of operation. So what is going to happen is I will have the equation beta n, whatever this is, VDD minus VTN squared. Basically, this is a constant current, okay? It doesn't change with time, okay? And when V out is less than VDD minus V, which is V sat, okay? I'm in linear mode of operation, and my voltage current relationship will be, the current will be VDD minus VTN minus V out T over 2 times V out T this way, okay? This is going to be my these are going to be my current values based on my output voltage value. As you can see, it's changing within time. Okay, the transistor is in cutoff, then enters saturation, and then as the voltage drops further, we are in the linear mode of operation. So there is no fixed current value, and what you need to do is basically solve these equations to arrive at a solution. Okay? And if we were to plot the graph, what's going to happen is this is my step input, as you can see here. Okay, this is my step input changing like this. What's happening is initially my current is 0, so there is no voltage drop, and then I'm in a current source mode of operation, saturation mode of operation. Fixed current means if this is a fixed value, this is fixed value, this is a constant, what will happen is V out will change linearly with time. Okay, this is what's happening. Okay, it's changing linearly with time, and then as V out drops, we will enter the linear mode of operation, and then basically the transistor acts like a resistor. Okay, remember that it was in the linear mode, the transistor was a voltage control resistor, where the control voltage was the input voltage. In this case, the input voltage is fixed, so it's going to behave like a constant resistor. And what's going to happen is basically the circuit will turn into a resistance and a capacitance. Okay, initially it is in the saturation mode, it is going to be like this. A capacitance is being discharged via a current source, and later on it becomes a capacitance is discharged via a resistance. So it's going to be bending over, okay, like this. This is the RC response, discharge response of a capacitance. I mean, if it's discharged through a resistor. And if you were to simulate this using a better model, okay, I mean, it is difficult to solve it by hand, as you see. And these are differential equations. It's difficult to solve at each time step, okay? By hand, it's going to be a lot of math. So instead, we use SPICE-like simulators to solve these kind of equations. And they can also use better models, okay? I mean, this is a very simplified model. And even with the simplified model, you see, you have to solve a differential equation. With more complex, more accurate models, you can think about the math, okay? I mean, it's not doable with hand. So what we can do is we can use simulators, SPICE-like simulators to do these kind of simulation, okay? And get the idea. And here you can see this one is the input and this one is the output, okay? And you can see the difference, okay? The 50% difference. This is the output, so this is the falling event. The fall delay is 66 picoseconds, and the rise delay is going to be has been found to be 83 picoseconds. Okay? That these kind of simulators will give you some idea, but you should not rely on, I mean, basically solely on these kind of simulators. So now the problem here is we cannot solve these by hand. Okay, simulators will solve, will give us an exact picture, or more or less exact picture of what's going on in time at the inputs and the outputs. Okay, but what we also want to do is we want to. I don't want to resort to a simulator each time. Okay, I also want to be able to estimate the delay easily. Okay, get an idea, which especially if I want to play with the parameters of my transistor. For example, if I change the width, if I change the length, what is going to happen? I want to know these kind of things. Okay, and in order to be able to get an idea of these things, you have to model it properly. I don't need a very accurate simulation kind of output picture. I am interested in only a certain point in this curve. Okay, I don't need to know what the voltage at this point is or this point is. I just need to know the difference at this point. Okay, these two events. Okay, when this one is 50%, this one is 50%, the difference at those two events. Okay, the shape of the curve, I am not interested. Okay, if I can come up with a model that gives me exactly what's happening or the delay between these two events, that will be very nice. Okay. And yeah, again, as I said, if I want to play with the parameters of a transistor, what's going to happen to this delay? I want to also get an idea of what's going to happen. Okay, I also want to make a what-if analysis. The step response, as you can see, looks like a first-order RC response with a decaying exponential. If you look into this picture here, here also, and here also, as you can see, this is a decaying exponential, and this is a rising kind of an exponential. Okay, so it looks like we can approximate that behavior if we can come up with, you know, what the capacitance here is. Okay, what this value is. If we can come up with this value here, then I will have a formula to make an estimate for the delay. And yeah, we saw that transistor is sometimes in saturation mode, okay, where it's acting like a current source, and then it's linear mode, and then it's acting like a resistor. So it's not a fixed value for this resistance. Okay. As I said, okay, C is the total capacitance at my output node, and I can use an effective resistance value for my R. Okay, based on the actual delay, I can come up with, if I know C, I can come up with, okay, if I know what the delay, I can get it from, let's say, from simulation. Okay, I know what my capacitance is. I can come up with an effective resistance value so that the delay is R times C. Okay, I know this value from simulation. I know this value, and I can come up with an approximation for this one. And then I can characterize transistors by finding their effective resistance. Okay, and this is going to depend on the average current as the gates switch. So what is this effective resistance? We know that the Shockley models have limited value, not accurate enough for modern transistors, too complicated for much hand analysis. Okay? Even these are simple models, they are too much complicated for hand analysis. What we can do is we can simplify. Okay, we are interested in the delay value. We can simplify the transistor, okay, into a resistor instead of having different modes of operation. It will, when it's open, it's a resistor. When it's closed, it's basically an open circuit. Okay, when it's closed, in reality, it was sometimes a current source and then a resistor. Okay, but now we will assume that, okay, when it's open, I mean, when it's conducting, it's it will have an effective resistance. And we can find this from simulation, okay, by simulating and then finding the delay. And if you know the capacitance, we can get an idea of what R is. This is going to be too inaccurate to predict the current at any given time, okay, as I said in the waveform here. This will not give me an accurate estimation of what the output voltage value or input voltage value or output voltage value at this point is. However, I'm not interested at that point. I'm interested at a certain point. If it is accurate enough at a certain point, that will be good for me. Okay? I'm not interested in drawing an exact picture of what's going on in time. So what we can do is place each transistor with an RC delay model. Okay, what we are going to use is we will use an ideal switch, okay, and a capacitance and an on resistance. For the unit NMOS transistor, okay, unit NMOS transistor, the minimum size transistor, or whatever you define it as unit, okay, size 1, let's say where W over L is equal to 1, you can say, for example, unit size, unit transistor, okay, or whatever you define as unit size, okay, that will be the minimum size that you will be using throughout your design. For a unit size NMOS transistor, the resistance is going to be R. For the same size PMOS transistor, I will assume that it is going to be 2R. The capacitances are the same, but the resistances are, the resistance is double, because you know that the PMOS transistor for the same size, okay, mu N C ox Wn over L. This is beta N for the NMOS, and beta P for the PMOS is going to be mu P C ox W P over L, okay? If W's are equal, the betas will be different. They will have the same C ox, we will different by the mobility values, okay? And we know that the PMOS mobility is 2 or 3 times less than the NMOS transistor. So what we expect is the resistance of the PMOS transistor to be 2 to 3 times bigger than the NMOS transistor for the same size, okay? So for a unit PMOS, we will assume 2R resistance, and for an NMOS transistor, we will assume R is resistance, okay? And here we see the drawings, what we are going to do, okay? This is my NMOS transistor. I will replace, if I see this in a circuit, I will replace this with this model, okay? The gate capacitance, okay, this is size K, okay? When K is 1, and K is 1, for K is 1, this is going to be C. Let me draw it here. For K is equal to 1, the NMOS transistor, okay, means that this is unit transistor. The model is going to be, I will have a, this is my gate, this is my source, this is my drain, okay. I will have a capacitance C here, okay, at my gate, and yeah, this is going to be my switch here, okay, an ideal switch, and here I will have another capacitance, which is again C, okay, K times C, this is 1, okay, this is my source, and here I will have a resistance and another capacitance. These capacitance come from the diffusion regions, okay, the drain diffusion and the this is basically the drain diffusion. This is the source diffusion region, okay. This is my drain point, okay, and here I have a resistance which value is R, okay. This is for the NMOS, and for the PMOS we will have twice for the PMOS. This is my source, this is my drain, this is my gate. Again, a similar model I will be using, okay. I am showing that these are grounded, but this is in fact going to be, yeah, let me do it the same way. So it doesn't matter actually, okay, whether it's grounded or not. I mean, as long as the it's VDD or ground, okay. As long as the voltages are still, okay, fixed value, you can assume they're all ground. This is going to have a capacitance to VDD, okay, value will be C, and here we will have another capacitance which value is again C. This is my source, and here I will have my switch, okay, which is here connected to my drain capacitance C, and this is 2R, okay. In this case, this is my drain. Okay? This is for unit size again. A unit size D by this is unit size, okay. If I increase the size, okay, if I make my transistor K times bigger, okay, if I have a transistor that is K times bigger, if this is instead of 1, I have here K, what will happen? The capacitances will increase by K times, okay. They will all grow by K times. And what will happen to my resistance? The resistance will drop, okay. I mean, K times bigger transistor means I can conduct K times more amount of current. So what is going to happen is my resistance will be K times smaller. Similarly, if this is K, this is K, this is K times C, my resistance will be K times smaller. It is like if it is like, okay, I am connecting, this is, let's say, 2R, 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 okay. I have K unit size transistors in parallel, okay, each having an on resistance of 2R. What's going to happen is, if I have K 2R resistance in parallel, the equivalent resistance is going to be what? It's going to be 2R divided by K, okay? That's the same thing, okay? If I increase the size of a transistor from 1 to K times 1, that it basically means I am putting K number of transistors in parallel, and the effective resistance will be K times small. This is these are the models that we're going to be using instead of actual transistor models for calculating the delay. Now let's look at what the R and C values are going to be. Okay. Yes, we said that, okay, we have a capacitance of C and a resistance of R, and what are the actual values for these parameters? The capacitance, C, we assume that the gate capacitance is equal to the diffusion capacitances. Okay, this is an approximation. This is not reality, but yeah, I mean, a good approximation. We can go with that. And for a gate with I mean, in 0.6 micron technology, this used to be 2 femtofarad per micrometer. Okay. Okay. I mean, if it's 1 micron, if you have a 1 micrometer, W is 1 micrometer, it means C gate is equal to 2 femtofarad. Okay. In 0.6 micrometer technology. But what has happened is with advanced technologies, this has dropped down to 1 femtofarad per micrometer. So it has reduced. Okay, and resistance is in the order of 10 kilo ohms. Okay, times micrometer in 0.6 micrometer process, and with shorter channel length, this has dropped down to 1.25 kilo ohms per times micrometer in a 65 micrometer process. So if I have a 1 micrometer transistor, again, 1 micrometer, W is 1 micrometer, what's going to happen is R is going to be 10 kilo ohms. Okay? And if it is 2 micrometers, for W is equal to 2 micrometers, for this technology, it's going to be, R is going to be what? 5 kilo ohms. Okay, I divided by the W value. So, and what do we mean with that? Unit transistor, we can say that, okay, the minimum contacted device. If lambda is 0.3 micrometers, it's going to be what? It's going to be 1.2 micrometer by, let's say, 0.6 micrometer transistor, okay? A unit size transistor, size 1, okay? Refers to this, where the channel width is 1.2 micrometer and the channel length is 0.6 micrometer. And in this case, if I say a size 2 transistor means what? A transistor which has a width of 2.4 micrometer and the channel length of 0.6 micrometer, okay? You do not multiply the size with the channel length. It's a fixed value, the minimum possible value. A larger size transistor will have a larger channel width, okay? You multiply the size with the width of the minimum size transistors to obtain the actual width of the, let's say, greater size transistor. Okay? Let's estimate the delay based on our RC model now, okay? If here we have an inverter driving another inverter, okay, where the PMOS transistor is twice the size of the NMOS transistor, okay? PMOS size is twice the size of NMOS transistor. So that what will happen is they will have equal amount of resistance, effective resistance, okay? If we draw the model, okay, we will be calculating the delay of this circuit, okay, an inverter driving another inverter, okay? This is an inverter driving another inverter, okay? This is my load inverter, and this is my driver inverter. So let's first start with plugging in the models, okay? For our first inverter, that's the driver inverter. Let's plug in the models for the NMOS transistor. What do we have? We will have a gate with a capacitance here. This is unit size. I will say this is capacitance C. I will have my switch. This is grounded, okay? Here I will have a capacitance. The other end is also grounded. Okay, this is C, this is my source, okay. Here I have my resistance, which is R, okay, R divided by 1. This is unit size, it's going to be R. And I will have here another capacitance. Okay, this is my output node, okay, Y, okay, Y. And here I will be drawing my PMOS transistor. This is here. Again, this time it's 2, okay, so this is going to be 2C, okay, twice the size. This is the gate of this one, and these one are connected, and this is A, okay. And here I have again my switch. Here I have my resistance, which is connected to here, and here I will have another capacitance. This is again 2C. Remember, this is twice the size. And this is going to be what? 2R over 2, okay? Which is basically R, okay? And since it's twice the size of the NMOS, unit size PMOS transistor has a resistance of 2R. If I make the size 2, the resistance will be 2R over 2. R. And here again, I will have a capacitance, which, and this is also 2C. And this Y is connected to the inputs of this load inverter. And what will I have? Okay, there will be one input capacitance coming from the first, the PMOS transistor, which is 2C, and another capacitor coming from the, remember this one I'm drawing here, from the load capacitance. This is C, okay? And I'm not interested in the diffusion capacitance. They are not connected to my node Y, okay? So these are, I'm trying to find out the delay of the first driver inverter, okay, from A to 1. So I'm not drawing the rest of this. This is my model, okay? This is my model that I'm going to be using to calculate the delay. Here you can see, okay, it's much clearer here, okay? This is R because the size is 2R over 2 is equal to R, okay? And these are 2C because the size is 2, unit size capacitance C, this is C, okay? So what do we see in this picture? This is the model where the output is being discharged to 0, okay? My PMOS transistor is off, okay, disconnected, okay, as you can see. My NMOS transistor is on, okay, and it is going to be discharging the output to 0. So this is basically modeling the delay, the falling delay of my driving input, okay, falling delay. The NMOS is on, falling delay, NMOS on, PMOS off. So I am interested in this path, okay? Whatever is connected is going to affect my delay value. And as you can see, what's happening here is, this is disconnected, so I'm not interested, bother myself with this part. Here you can see a capacitance for which the both inputs are connected to ground, okay? Both inputs are grounded, so this is an irrelevant capacitor. So the voltage at neither ports is changing, no terminal is changing. Okay? They are at the same voltage, so there is no voltage change here. This can be ignored, okay? And similarly, this one, although this is at this point when the NMOS is on and PMOS is off, this is, you can ignore this one. This can also be ignored, okay? This part is totally ignored. Now, this part is the relevant circuit that will affect my falling delay. And you can see this is my resistance. This is going to be equivalent to what? A resistance pulling the output node Y to ground, okay? And VDD or ground doesn't matter as long as these voltages are a fixed value. You can assume they are all grounds, okay? So what is the total capacitance at this node? It is going to be C coming from this one, let's say 2C coming from this one, 2C, and C and 2C here, C and another 2C. These are coming from the load. These are coming from the diffusion capacitances of the of my driver transistor, okay? And these are capacitors that are in parallel. So the total equivalent circuit will be, this is, I have a resistance, and if I have capacitances in parallel, I can simply add up the capacitance value. So this is going to be an effective, or the total capacitance. This is R, C, 2C, 3C, C, 4C, 2C more, it's going to be 6C, okay? So I have a circuit, an RC circuit, okay, a resistance of R, a capacitance of 6C. So the total delay I expect is to be what? T, F, okay, it's going to be what? 6 R. Okay. This is simplified into this. And as you can see, the delay is going to be what? The falling delay is going to be 6 RC. Okay, this is how you're going to calculate. And if you do the same calculation for the rising event, you will see that it's going to be the same, okay? I mean, it doesn't matter, okay? It's going to see, again, the same amount of capacitance here, and the resistance is the same, so the rising event, rising delay will also be the same value, okay? Again, you will ignore this one, and this part of the this part of the circuit will be ignored, okay? So if we were to compare the models of the that we know so far, okay, we have a simulator, we have the Shockley model, the simple first order model of a transistor, and we have our RC model. And if we were to plot these, you will see these curves, okay? The blue one is the Shockley, the black one is the SPICE model, the actual delay graph, and the dashed one is the RC model prediction. Okay? As you can see, it's somewhere between the Shockley and the SPICE results, but it is pretty much close to the actual SPICE results. As you can see here, for example, the results of our RC model deviate a lot from the actual results, okay, or either Shockley or SPICE models. But this is not important, okay? We are not interested at this point for the delay at this point. We are interested at the delay value at this point. So if I can estimate the delay using my RC model at this point accurate enough, that will be good enough for me. And as you can see from the graph, it is good enough. And here we have another example. A 3-input NAND gate. We are asked to sketch a 3-input NAND gate with transistor widths, okay, or transistor sizes chosen to achieve an effective rise and fall resistance equal to a unit inverter. Okay. Remember, what was the rise and fall resistance of our unit inverter? Okay, this was our unit inverter. Okay, this is our unit inverter, and we saw that the rise and fall resistances are both R. In order to achieve these values, we made the PMOS transistor twice the MOS transistor. So we want a 3-input NAND gate which has similar rise and fall resistance. Okay, when one of the inputs is turned on. Okay. And what we want is, I want an effective resistance of R here, and that is going to be R up, and an effective resistance of R here. This is R down. They should be equal to R. Okay. So how can I find this? Okay, how can I make them equal? If, for example, the sizes of my transistor, if this is selected unit size, what will happen? This is going to have a resistance of R. This is R, and this is R. Okay. So, and these are in series. So what do I have? I have an effective pull down resistance of what? This is going to be in series 3R. Okay. And if, for example, I have size 1 here, okay, I'm assuming for this path only, okay, and if I assume one of the transistors is on here, okay, not all of them, but one of them is on, what I have is I have just one transistor with size 1. This is a resistance of 2R, okay, and this is going to be equivalent to what? R. As you can see, they are different, and they are also not R. Okay, remember, for the inverter, what did we have? This was size 2. This was size 1. Resistance here was R. Up was R. Resistance down, R down was again R. Okay, and in our, if I make all the transistors unit size, in my NAND gate, okay, I end up with a solution where the up resistance is 2R and the down resistance is 3R. So in order to make them R, what do I need to do? I basically need to, in order to make this one 3R and R, I need to divide this by 3. And how can I do that? If I have resistances that are 3 times smaller, okay, 3 resistances with the value R over 3, I will end up with a resistance of 3R over 3, which is going to be R. Okay, so in order to achieve 3 times smaller resistance, what I need to do is I have to multiply these sizes with that value, which is going to be what? This is going to be 3, this is going to be 3, this is going to be 3, so that I can have a resistance of R over 3. Similarly, for the PMOS transistor, this is 2R. In order to achieve a value of R, I need to divide by 2. So basically, I need to divide this by 2, and I can do this by multiplying the size by basically 2. Okay. So the result is going to be what? Here, the PMOS transistors will be of size 2, and the NMOS transistors will be of size 3. And if we look at the capacitance values, how much capacitance do we have at the input and the output node? Let's calculate that, an intermediate node. Here I have a size 2 transistor, means that this has a capacitance of 2C, okay? And at the same node, this is a size 3 transistor, so this is going to be 3C. So 3 plus 2 will have a total capacitance of 5C. For each input, this is the case, okay? For each input, I have 2 transistors connected, one PMOS and the other one an NMOS. The PMOS transistor size is 2, the NMOS transistor size is 3, so the total capacitance is going to be 2 plus 3, 5C for each input. And let's look at the output. At the output node, here I will have the capacitance of 2C. Here again a 2C. Here it's going to be 2C, and from here I will have the capacitance of 3C coming from this transistor. Okay, and in the intermediate nodes, again 3C capacitance. Actually, it's going to be 6C. Okay, 3C coming from this, 3C coming from this, 6C. Let's write it down like 6C. But with proper layout techniques, okay, we can reduce this down to 3C. Okay, that's why it's written as 3C. It's normal, it's going to be 6C. Each 3C coming from each transistor, it's going to be 6C, but with proper layout techniques, we will see what that is later on. We will assume that it is going to be just 3C. So 2C, 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 3C. So at the output, I have 9C capacity. Now, as you can see, what's going to happen here is, if I want to find the delay from this input, for example, okay, what's going to happen is, at the output, I will have a capacitance, okay. Okay. And here I will have a capacitance, here I will have a capacitance. This is R, let's say this is R over 3, pardon, R over 3, R over 3, okay, and these are 3C, 3C, and this is going to be what? 9C, okay? So this is not like the RC delay network we have, okay? Remember that we know how to calculate the delay for this kind of a circuit, where I have a single resistance and a single capacitance. The delay is going to be R times C. What if I have this kind of a network of capacitances and resistances? Yeah, in order to find the delay of this, we will be using a delay formula called the Elmore delay formula. Okay. The formula is like this. If I have a network of resistances and capacitances here, and if I have a step input here, the delay will be R times C1, okay, R times C1, plus R1 plus R2 times C2, okay, plus R1 plus R2 plus R3 times C3. So basically, the total resistance this capacitance sees through the signal source, okay? I'm adding up all those values, and this is going to give me my final delay value. R1C1 plus the resistance this between this capacitance and my signal source, R1 plus R2 times C2, plus the resistance between this capacitance and my signal source is going to be R1 plus R2 plus R3 times C3, blah, blah, blah. And for the final capacitance is going to be Cn, all the resistance, summation of all the resistance up to Cn, okay, will give, and if I add up these delay values, I will add up at my final delay value. And what we did here is we have modeled the pull-down network as a RC ladder network, okay? If you tilt this one, you will see that it's going to look like an RC network. At this point, I will stop.